Hope you guys are doing well. Happy Wednesday. Quick reminder, we'll meet for lab tomorrow. We'll meet again at 11. We'll get 2 labs in pretty quickly. Today we are going to talk about capacitors in circuits. This will be... hopefully this will get us through the rest of the math information for Chapter 16, and we will be utilizing this information in lab tomorrow. And so then Friday we'll have a free review day. Make sure everyone's to work on your homework and to ask any relevant questions as you're going through that. Let me know if there's any questions, problems, concerns, etc. right now before we get started. All right. If not, then let's go ahead and get started. All right, so we talked about what capacitors are, what builds them, what function they serve. Now we're going to sort of look at how they are practically arranged in circuits. A lot of electricity, a lot of the concepts surrounding electricity have been compiled and combined together to create sort of circuits in most modern electronics as we currently understand them. Every individual piece of a circuit, every component you see on a circuit board is the result of combining a bunch of these electrical concepts together into the various components that serve their various purposes within the machine. Capacitors are just one of the components that you could see within a circuit, one of the parts that could be built into that circuit board. And their function within the circuit board is to hold on to energy, to hold on to charge. They do that by storing the charge in the electric field between their two plates, and that charge is sort of slowly fed out of the other end as time goes on. It sort of banks that charge up, it builds it up, and then slowly releases it over time, often in a controlled way that the circuit is able to calculate and handle, kind of as a way to adjust, say, the amount of power going to one part of a circuit or another. So, very, very useful. It's fair to say that without capacitors, modern electronics as we currently have them wouldn't really exist. I'd say transistors are probably credited as the big one. We won't really cover... Transistors are a separate machine, but capacitors are also very important. In fact, the original touch screens were based on capacitors, and so without them, we wouldn't have been able to advance to the current touch screens that we presently have, which are more resistance-based. What you're currently seeing on screen is 2 elements of a circuit diagram. Let's see if I can skip ahead to a different circuit picture just to kind of show you what we're going to work towards first. I'm jumping ahead a little bit just to show you a sample circuit diagram. You might have seen drawings like this. Maybe you've just seen drawings like this, like in textbooks or in science classes before, or maybe even in movies or in a laboratory setting. This is a very basic circuit diagram. And, wiring in a house. You might have seen electrical diagrams there too. And the purpose of a circuit diagram is to show how all the various components of a circuit are wired in together, because the way in which things are connected is very important to how the electricity flows through the circuit, how it flows through each of the components of the circuit. In this particular diagram here, this blocky thing down here is the battery. This this picture physically resembles a car battery. So when you open the hood of your car and you see the big square thing with the leads on it, that's the car battery. This is what supplies the voltage to the circuit. Batteries are commonly referred to as voltage supplies for that reason, since voltage is kind of what the equivalent of water pressure that drives electric currents to move. You have to hook a battery or some other voltage source up to a machine in order for its circuitry to actually run. Without that voltage, without that water pressure, there's nothing to push the current from the positive side through and back to the negative side. So all circuits need a battery or some other voltage source. And you can see here that this battery is labeled with the amount of volts that it supplies. From there, you draw lines to represent where the current comes out of the battery and then what components it then flows to. So in this particular circuit, current flows out of the positive end, comes up here to this junction, and then it'll split off and flow through one of these other capacitors that are present. This symbol here, the symbol of the two parallel plates, is the symbol for a capacitor, which is consistent with how we've been drawing them so far. They need to have two parallel plates that have an E field between them to be a capacitor, and so that's the symbol that we use for them in the diagrams. So two equally sized parallel lines is a capacitor in these drawings. Current's going to flow through here, hit this junction, and then it'll flow it'll split off here, kind of like how a river will split, flow through one of the capacitors before rejoining and then flowing back to the battery. So kind of using this drawing as a sample real quick, circuit diagrams need a voltage source, they need to show wiring connecting all of the circuit components, they need to show what components are present and sort of the order in which the current will flow through them, and always the current has to flow back to the voltage source. If, hypothetically, you were to cut the wire right here, if you were just to physically slice it, and there was just a break there, then the entire circuit would stop. Because the electricity needs to be able to flow back to the battery. If this connection was broken right here, you wouldn't have a complete circuit. This would be like if you only attached one jumper lead to your battery and expected it to work right. You need the second lead. You need a connection out of the battery and then back to the battery, complete, successful, unbroken, for the circuit to actually work right. So those are kind of the primary essential parts of a circuit diagram. If a diagram doesn't have those elements, battery, wires, fully connected from start to end of the battery, and the various elements in between, then it's either not a very good circuit diagram or it just won't work. And so we're going to begin the process of examining circuit diagrams. This is going to be sort of our introduction to it as we go on and before we start next week and looking at more complex diagrams. Just starting with capacitors and batteries. So, jumping back to the first slide again, what we've got here is two symbols that are commonly used to represent capacitors in a drawing. So again, two parallel lines that are the same length represents a capacitor. The images in these notes usually have a physical picture of a battery representing the battery itself, but there is a shorthand symbol for it so that you don't have to draw a battery out every time you are making a diagram. That symbol is two parallel lines that are not the same size. One of them has a positive and one of them has a negative. This again represents that the battery must have one positive side, one negative side, and then it represents the voltage supply, the potential difference within the circuit. So, we're now going to begin examining circuits and kind of how capacitors work together in a circuit. Now, I'm jumping back a little bit. We kind of already know what a single capacitor all by itself will do in a circuit. We know this because of this original capacitance formula, C equals charge over change in voltage. If you just hook one single capacitor up to a battery, let's see if I can actually make a quick circuit diagram for that. So this is going to be a very quick diagram. This is hypothetically the simplest capacitor circuit that you can build. We have one battery connected directly to one capacitor that is then connected back to the negative end of the battery. Again, simplest diagram you could have. Just one battery feeding around to itself through maybe one component. And we already know what will actually happen in this circuit because of this particular formula. The battery will supply some amount of voltage. That voltage will generate a certain amount of charge within the capacitor based on its capacitance. So if you had a 1 volt battery and a 1 farad capacitor, then that capacitor would build up a maximum of 1 coulomb of charge when wired into this specific circuit. So 1 battery, 1 capacitor, this first formula here represents everything that's going to happen. Things start getting more complicated if you were to put more than 1 capacitor into your circuit. Because there's several different ways to draw circuits, several different ways to design them. The next most straightforward type of circuits to build, the one I showed a second ago with just 1 battery and 1 capacitor, is easily the simplest design of circuit. This is the next most simplest design. I'll actually draw in the diagram version of this just so that you're more accustomed to seeing those over time. So this would be the version of the picture that's just using the symbols as opposed to more literal pictures. Rather than just 1 capacitor, this particular circuit has 2 capacitors, wired one right after the other. And this type of a circuit is called a series circuit because the elements in question, these 2 capacitors, are wired one right after the other. They are literally in a series. The current, so if we follow the current through this particular circuit, any current that exits the battery has to go first through the first capacitor, and then it must then go through the second capacitor and then back to the battery. There's no possible variation. The current has to go through them in sequence. And so that's why it's called a series circuit. All series circuits share this functionality. It doesn't matter exactly what components are wired in series. As long as they're in series, the current has to go in a straight line through one, through the next one, and then back to the battery. You could even hypothetically chain more than 2 together. I see 3 or 4 in series pretty frequently. So just the vocab word to keep in your head as we will eventually move on to other components in circuits and more complex circuits is series circuits require all the elements wired in one straight line, one straight path. The electron flow, the current flow, has no choice in what path to take because there's only one path. It's like a river that doesn't split. Everything has to flow in a straight line from point A to point B. And when capacitors are teamed up like this, something kind of weird happens. You would not be wrong in expecting the 2 capacitors to sort of just team up, to add up together to form a greater capacitance. which would make an amount of logical sense. They go one after the other. They should probably logically kind of team up together. But that's actually more the logic of what's going to happen to resistors when we talk about them next week. So if you've done much circuitry before, you might be remembering resistors, if that's sort of what you're thinking. What actually happens with capacitors in series is, rather than sort of teaming up to form a greater capacitance, they actually sort of work against each other and overall create a lower capacitance than either would by themselves. The way that you add up these capacitances is, rather than just adding them up directly, like say you wanted to find the total capacitance of this entire circuit so that you could try to find the total amount of charge stored up in this entire circuit, rather than adding C1 and C2 together linearly, you instead take the reciprocal of the sum of their reciprocals. So you add up 1 over C1 plus 1 over C2, and whenever that sum is, you invert it again. So it's the reciprocal of the sum of the reciprocals. Again, if you've worked with resistor circuits in a previous science class, this may look familiar. That's my goal. So capacitors wired in series work against each other and end up creating a net overall lower capacitance than either one working by themselves. And it's due to the fact that they kind of interfere with each other. The first capacitor kind of slows down the current in the entire circuit, thus making the second capacitor develop less charge, or at least more slowly, since the current is kind of being held up by the first one. And there's just this feedback loop where they don't get along well and they work against each other and kind of reduce their overall effectiveness as a result. I want to show our first sample calculation for this. So, here's a slightly different series circuit. We have one battery connected to 4 capacitors in series. They are all still in series with each other because the flow goes one right after the other. And they all have different capacitances. We've got 3, 6, 12, and 24 microfarads. This is the symbol for the metric prefix micro, if you haven't seen it in a while. Micro is times 10 to the negative 6th. And let's just calculate the total capacitance of this particular circuit. So again, in series, we do not add them up linearly. We have to add up their reciprocals first. So rather than 1 plus 6 plus 12 plus 24, it's going to be 1 divided by 3 plus 1 divided by 6 plus 1 divided by 12 plus 1 divided by 24. You take that sum. I've already done... when I was doing my math, I went ahead and simplified it down to its simplest form. That summation here is equal to 5/8. So that is already the sum of the reciprocals. All of these inverted fractions will add up to 5/8, but that itself is not the final capacitance. Because the formula is 1 divided by the total capacitance is the sum of all the reciprocals. So 5/8 is 1 over the total capacitance. To find the final total capacitance of all these capacitors working together, you need to then invert it again. And there's a couple different ways you can do that. You could raise both sides to the negative first power. That's one legal technique. In my brain, I just tend to literally visually swap both sides upside down, which is also a legal move. So instead of 1 over C total equaling 5/8, we have C total over 1, is also a legal way to write that, equals 8/5. So just both sides swapped upside down. And that's going to give us a grand total of 1.6 microfarads. Two things to note here. One, I didn't convert these into normal farads first. If you were to do that, just note that the unit you get out will match the unit you put in. So if you plug microfarads into this formula, you will get microfarads back out. So I kept everything in microfarads. My answer is presented in microfarads. The other thing to note is this final total capacitance, 1.6 microfarads, is less than even the smallest of the capacitors presently in this series pattern. Due to the way that they add up in this orientation, since they kind of work against each other, they reduce their overall effectiveness. The total capacitance is driven down in series because of the way they add up like this, because of the reciprocal addition. So capacitors in series are kind of really weird, technically speaking. It's okay if the logic for this, if the math for this takes some time to sink in. It's one reason why we're going to work on it in lab together tomorrow. But that is capacitors in series. Why are multiple capacitors in series? They can add up to one total capacitance that represents the entire circuit's capacitance, but it will tend to be less than even the smallest of the capacitors involved in the series circuit. Let me know if you've got any questions or issues right now. All right. So series circuits tend to be the physically easiest to build simply because you just wire one component right after the other. It's like just building a straight line of Legos, just one piece connected immediately to the next piece. There is a different way to build circuits, a different orientation to design a circuit. And rather than series, we call this pattern a parallel circuit. So here, we have our battery. That's unchanged. Every circuit needs a voltage source. Current is going to flow out of that battery. And then rather than go through both components one after the other, we've built this into sort of a ladder rung configuration where we have two parallel branches. So at this point right here, at this junction that I've circled, the current could either go down this path or it could go down this path. It splits at this junction. It'll go through either C2 or either C1. It can't do both at once. Once it splits, it has to go through one or the other before the two paths reconvene at this junction right here. This would kind of be like if a river splits and after splitting goes to two separate water wheels along each different path, and then after passing through each water wheel, the rivers reconvene back into their original river. So again, this is called a parallel circuit because of its two separate parallel rungs, parallel paths that the current could follow. And real quick, I will draw this as a basic circuit diagram without the extra images in it, just so you can kind of see what that looks like. Try to draw the capacitor lines bigger than the battery. So, pretty common way to draw parallel circuits. We have our battery. We have two parallel rungs that contain the two capacitors, and then they will reconvene back to the battery. I'm going to pause right here real fast because I actually have to go to the restroom. So I will be right back. If you have any questions, formulate them while I'm gone. Any questions, needs, etc. before we continue? All right. So, parallel circuits are arguably harder to build because you have to make sure that your connections are in such a way that you create multiple branching pathways. But weirdly, the way that the capacitors sort of add up together in this circuit diagram is actually a lot more straightforward. Capacitors in parallel, to find the total capacitance of the entire circuit, you actually just add the capacitors straight up linearly. Whatever C1 is and whatever C2 is, as long as they're in parallel, the total circuit capacitance is just their normal, usual sum. It's just straightforward. And the reason for that is since the two branches are now parallel, they can have current feeding into them at the same time. They don't interfere with each other like the other configuration would. So they're able to charge up separately rather than sort of one at a time. So capacitors work better together in parallel, whereas they work against each other in series. So, sample question. What would the effective capacitance of this circuit be? This is actually the same three capacitors as the previous example. We've got 3, 6, 12, and 24 microfarads, and these are all in parallel. We've got a battery here connected to the rest of the circuit. The path is going to split right here into one of 4 different paths. Each capacitor is on its own separate branch. Current will meet back up here before flowing back to the battery. So this is a parallel circuit, and that means that all these capacitors, we can just add them up together. So 3 plus 6 plus 12 plus 24 will give us a total final capacitance of 45 microfarads. Again, you can keep it micro for the sake of just this simple part of the math. It just means that you'll have micro out the other side. You will have microfarads as a result. And most like industrial commercial capacitors that you would again be able to buy at a store to then like use in your own home projects, most capacitors are around the microfarad range. They tend to be pretty small. So, those are the two primary ways that circuits can be built, and those are the two ways that capacitors work together, add up in those circuit orientations. Now, separately, those two circuits are straightforward enough. They're pretty easy to identify, and they each have their own specific separate methods for calculating total capacitance. Things get a little more complicated if you built a mixed circuit. Because if you've ever looked at electrical diagrams, they don't always tend to be very simple. There tends to be wires and components arranged in all kinds of orientations, oftentimes kind of hybrid methods that are, some parts of it are series, some parts of it are parallel. For example, in this particular circuit, which we will work together, I'm going to show how I would recommend tackling finding the total capacitance of this particular circuit. Let me try to draw in the rest of the circuit real fast. So this is our battery. Current is going to flow out of the battery towards junction A. After hitting junction A, it's going to split at this junction. It can go down this pathway where it'll meet C1 and C2, or go down this pathway where it can meet a different version of C1 and C2, or it can go down this pathway where it will just go through one version of C3. They'll meet back up before coming here and splitting again. Here it'll go through either one of two different C2s before meeting back up, hitting junction B, and going back to our battery. This is a hybrid circuit. There's parts of it that are series and parts of it that are parallel. And we can find the total capacitance of this mess. It just takes some doing. I'm going to show the method that I would recommend for analyzing circuits of this type. Basically, you kind of have to start simplifying it one piece, one rung at a time. So this here is me redrawing the entire situation, and I've put all the numbers in this time. Rather than just saying C1, C2, etc., I've replaced that with the actual numerical value of each one. C1 is 5, C2 is 10, C3 is 2. So I've written all the numbers in instead. I find that that helps a little more. And I find the best way to simplify these is to take it just one step, one piece at a time. For example, if we were following the current along this circuit, so this is our A junction, and this is B junction. We're going to start up here at A. The first thing that happens is the current can go down, one of 3 different pathways. In 2 of those pathways, 2 of the rungs that are formed here, we have one 5 microfarad capacitor in series with a 10 microfarad capacitor, and it mirrors that here on the other side. The third pathway is just one 2 microfarad capacitor, and that's before they all rejoin back here at this piece. So I've labeled this left branching path as branch A, and this right branching path as branch B. Now, A is parallel to B, and both are parallel to the 2 microfarad capacitor. So this option, this entire branch, is parallel to this entire branch, and they are both in turn parallel to this whole branch. So those branches are all parallel to each other. We should ultimately be able to add all those branches up linearly together. But before we can do that, branch A has 2 different capacitors in series on that branch. So if the current branches towards branch A, it goes through the 5 and then also must go through the 10 before it rejoins. So branch A is a branch that is parallel to branches B and the 2 microfarad capacitor, but it itself has some in-series elements on its branch. So before we could ever try to add A and B and the 2 microfarad capacitor together as if they were in parallel, we would first have to figure out what branch A's actual total capacitance is first, because what's parallel here is completely separate rungs. Rung A is parallel to rung B, but each of those rungs has a series circuit on it. So before you can add the rungs together in parallel, you have to figure out what each rung's total series capacitance is first. I might be over-explaining. The math that I do here is, for rung A, over here labeled under A, rung A might be in parallel to other stuff, but it is itself a series circuit with a 5 and a 10 on it. So I performed the series math on that 5 and on that 10. So 1 over capacitance A is equal to 1 over 5 plus 1 over 10. This would overall give us a total capacitance for all of rung A combined of 3.3 repeating microfarads. This makes sense with our earlier observation. In series, with the reciprocal math, the total capacitance tends to end up being smaller than the smallest physical capacitor on that branch. And 3.3 is smaller than the smaller of the 2 on this particular branch. So this is an answer that we would come to expect. This is consistent with what we would expect here. So branch A is functionally, we can basically combine this 5 and this 10 together to functionally create and replace them with a single 3.3 microfarad capacitor on this drawing. Likewise, branch B has the same orientation of capacitors in series, so branch B would also be 3.3 repeating microfarads as well. And I'm going to actually show a simplified drawing for that in a minute. Real quick though, down here, this whole section has two 10 microfarad capacitors still in parallel with one another. These 10s are just in parallel with each other, so their relationship with each other is only parallel, and in parallel, the two will just add up normally. So what I'm calling here part C, I've just boxed off these two capacitors together. They're in parallel with each other, nothing else is going on there. They will functionally team up to create a single 20 microfarad capacitor. So we've begun the work of simplifying this. We've determined what the total capacitance of branch A, branch B, and branch C are. Once you've found the total capacitance of a specific branch, you can basically redraw the picture, simplifying that branch down to only a single capacitor of that total capacitance. So in my next drawing here, I've simplified all of A and all of B down to a single 3.3 microfarad capacitor each. So this part here is what used to be A. This part here is what used to be B. And I'll tap back real quick to show. I've replaced within the drawing the 5 and the 10 with their added sum right here. And after doing that step, instead of having 5 capacitors that are all in different relationships to each other, we've simplified it down into 3 capacitors that are all in parallel with each other. So the 3.3, the 2, and the 3.3 are once again completely normally in parallel with one another. There's no part of this that's in series with a different part of itself. So this little section here that I've labeled part D is just parallel. I've also simplified what I labeled part C earlier down into just the 20 microfarad capacitor. So this piece here used to be part C. But looking just up at this boxed section, just these 3 that are in parallel with each other, they're now parallel. There's no weird series part of it. It's just 3 separate rungs in parallel with each other. That means we can add them up normally, linearly, as you do with parallel capacitors. So that means that section D, which is these 3 rungs here, A, B, and the 2 microfarad, can add up normally to become 8.66 microfarads. And once we've determined that, we can replace this entire section with a single 8.66 microfarad capacitor. So we're sort of strategically simplifying things down one rung at a time. We're trying to remove complexity by finding what a certain section's total capacitance would be and replacing that section with a single capacitor of that capacitance. After replacing D with the 8.66, well, now that whole section, that 8.66, is just in linear series with the 20 microfarads. Which means we can do the reciprocal math to add them up like they're in series with one another. So 1 over total capacitance is 1 over 8.66 plus 1 over 20. Perform that math and we'll eventually end up with a total net final capacitance of 6.05 microfarads. What this tells us is the entire original circuit, all of these capacitors wired together in this configuration, could be replaced. You could rip all of them out and replace them with a single 6.05 microfarad capacitor, and the net effect would be exactly the same. The circuit would generate the same amount of charge for the same amount of voltage if you just had one 6.05 microfarad capacitor in it. All of the previous capacitors have teamed up, added up together to create this final total. And so the result of hybrid circuits, after sort of simplifying them down one piece at a time, is you can get one total final effective capacitance that represents sort of the one capacitor you could replace all of the previous ones with to get the same net effect. All hybrid circuits can be treated in this way, simplified one piece at a time. But every hybrid circuit's a little different. You'll have to sort of tackle different rungs in different orders, depending on its orientation. And that's one of the things we're going to work on together in lab tomorrow, is working on more examples of hybrid circuits together to kind of get some practice in for it, kind of help develop your skills at working on circuits in general and how to examine the way that hybrid circuits work. It's okay if the hybrids are weird. They take time. They take analysis, and that's why, like, a hypothetical test question about this would only have, like, maybe one hybrid circuit on it, and the point of the question is just, what do all of these add up together to form? So we'll be working on this skill together tomorrow as part of our lab activities. And with that, that is all the math and new information of Chapter 16. So tomorrow we'll be utilizing this stuff in lab. Friday we'll take a day where you can work on homework questions, and I'll be here to help you out with anything that comes up. And then next week we will move on to Chapter 17, which will be about even more circuits. Any questions, concerns, needs, etc. at this particular time? All right. In that case, I'll be in this call for the next hour. If you have questions, I recommend you take a break and then look over your homework for a little while. And if I don't see you again today, I will see you for lab at 11 a.m. tomorrow. Have a nice day.